So this will be bringing software-defined radio to the penetration testing community. Let's give our presenters a small hand of applause. Thank you.
Thank you. So my name is Jean-Michel. Here is Arnaud. We'll present you a tool that we have been developing for quite a while to help pen testers to assess radio frequency communicative equipment. So the first constatation we made was that more and more connected objects are coming to the market. The stat is from Cisco, and as you can see, it grows pretty fast. Second thing, and that was the main topic that led us to develop that, is regarding smart meters. The stat is from the US Energy Information Administration. The main risk with those devices is that the devices will be at your home, so you do have physical access to the device. Plus, it's provided for free. The energy company is just giving you a device. And fraud is not the main issue with that. That's not what the energy company is fearing. What they fear is you to be able to compromise the firmware of those smart meters and being able, for example, to shut down a whole neighborhood. Because they will produce energy and it cannot be stored, so the energy has to go somewhere. So if you shut down, you're just raising up the gap between what's produced and what's been consumed. Moreover, after we started our development, we saw a draft from the NIST stating that basically there was a tool that was missing using a software-defined radio from Ethos Research to do the RF analysis. And that was exactly what we were developing, so we decided to release the tool, and that's why we are here. So what are the challenges? Challenges with radio frequencies that you have to face up multiple radio protocols. For example, smart meters, you can have smart meters communicating with Zigbee, but you can also have HART, -7, you name it. You also have to deal with multiple bands of frequencies. Most of the time you will face the ISM band, but still it goes from 453 megahertz up to 2.4 gigahertz. So it's still too wide to be able to deal with that with only one transceiver. And in addition to that, even though, for example, WM bus can transmit on the ISM band, it also has a proprietary frequency to transmit on. You also have multiple modulations, FSK, PSK, ASK, you name it. So it's pretty hard to deal with a transceiver that has been hardwired. And you also have multiple bit rates. All those things make somehow difficult to deal with radio frequency in a common way, like we can do on traditional pen testing with Ethernet. And you also have multiple applicative layers. That's, for example, for the .15.4 protocol on which Zigbee is based. This protocol just gives you the lower layers, but you can define your applicative layer on top of that, and Zigbee is one of that. The existing tools to deal with radio frequency so far that are quite close to what we are doing. You have the Bluetooth from Michael Osman, but it's dedicated to Bluetooth and Bluetooth low energy. So you're somehow limited with that. You also have the RFCAT by Atlas of Doom, and this one is maybe the closest to what we are trying to achieve. But it's only compatible with a subset of chipcon-based dongles. So it's just a transceiver which is made to deal with ISM band, and you flash another firmware on it, and then you're able to deal with sub-gigahertz ISM band and just configure it with a Python interactive shell. 2.4 gigahertz, I think Atlas is trying to develop it, but I don't know, I don't think it's released yet, and it's still figuring out which dongle it will use. And again, it just grabs you raw packet. You set a frequency, you set a bit rate, you set the modulation, the packet length, and then you just have raw packets. You don't have the understanding of upper layers. And for ZigBee, you have the API mode, for example, that has been developed by Ray and Spears from Rival Loop Security. Fortunately, right now, computers are going more and more efficient. So we can move from what has been done in hardware, move it to your CPU instead. And that's why we are dealing with software-defined radio. It is basically a configurable local oscillator. No hardwire processing is done. You just have a local oscillator, preamplificators, filters, and an ADC, an analogic to digital converter. It will just stream some raw digital samples to your computer, and then your CPU will do the rest. It comes from $20 up to $10,000, maybe more. The compromise we've found between the size of the appliance, the performance, and the price is that you can just grab a software-defined radio card from $300 to $1,000, and you'll be fine. And it became very popular and affordable since RTL SDR. Those are the ones for $20. It's just a USB TV receptor that has been hacked by the driver to be able to stream samples, but it can just receive. And all can listen, but some also can send, and that's the deal. You have the HRF by Michael Osman. Maybe some of the luckiest from you have taken this his training from the few days before. You have also the USRP from Ethos Research. Balin Sieber from the Ethos Research will probably show you some stuff with that card tomorrow on his briefing. This one has the particularity to be dual channel. With HRF, if you want to use a HRF with our tool, you will need to have two cards because it solves duplex. So you will need one card for reception and one card for transmitting packets. With USRP, you have dual channel, so you can do full duplex with two channels at once. But our tool will just use one. And finally, you have the Blade RF, which can do just receive and transmit on one card. So let me introduce GNU Radio and SCAPI, that are the two main components of our tool. And has anyone in the audience play with GNU Radio? Quite a lot. And with SCAPI? Almost the same. So GNU Radio, it's a framework. You have a click-and-play GUI, which is called GNU Radio Companion, where you can just assemble basic blocks. Those are the picture you can see on the right. You just have basic blocks that do specific computation, and you just connect them together to do what was done in a DSP, for example, in a digital signal processor. You can extend it with the helper grmod tool. You can extend it coding in Python or C++, and it supports a lot of SDR. At least the three I was mentioning on the previous slide are fully supported. And you got a lot of great tutorials, plus Michael Osman training, like I mentioned before. Basic blocks are also available to do blind signal analysis. It's pretty neat, because once you're dealing with an equipment, sometimes you know everything about the radio protocol at the radio frequency it will communicate on, but sometimes you don't. So it's pretty awesome to have some kind of block, so you can just do try, fail, try, succeed to bring your graph working and receiving packets. And of course, it's open source. It's GPLv free licensed. So basically, it's just a signal processor that works like a Lego game. It's just as easy as plugging and connects blocks together. For SCAPI, it's an interactive packet manipulation program. This quote is taken from its website. It's used, I think, worldwide by pen testers because it's provided on a lot of Linux distribution. It's full Python code. and it's supported in Windows, Linux, Mac OS X. It's easy to extend. You just have to bring new Python classes, and that's all. And it supports a lot of protocols right now. It has native fuzzing capabilities, so it can speed up your pen test. When you're just adding a protocol, you can use the basic fuzzing capabilities of SCAPI and find a crash or things like that. And you also have some high-level tools available based on SCAPI. For example, like we will see later, automatons, and you also have external programs. So let's talk about our tool, SCAPI Radio. How does it work? It works with SCAPI, of course. A lot of layers implementing your packets for the given protocols. You have your software-defined radio on the other side with GNU Radio Graph, the GRC. GRC is the file from the picture with the blocks connected. This is the file produced by GNU Radio Companion, and this is the flow graph to process your packets. SCAPI will fork to launch GNU Radio on the background, given your RF protocol you want to launch. SCAPI provides you a way, which is called a super socket, to change the physical layer. So that's what we are using right now. You have to provide an input socket and an output socket. So we have implemented a class for that. And GNU Radio on the other side will provide you the exact same socket to connect them together. And we used UDP plus a custom header to identify the protocols for the communication. Recently, we wanted to play with to dynamically change the behavior of the GNU Radio graph. And GNU Radio provides an XML RPC server that can be leveraged to do that, to change variables, and it will reconfigure your graph dynamically. So we added that channel. Why using a UDP socket? Well, first, it's natively supported under GNU Radio. It also supports TuneTap, but this one requires root. And we didn't find any reason to have to run our tool under root privileges account. So UDP was fine. And creating our own custom interface didn't sound a good idea. Plus, it's easy to forward. If you think of that, you can have a computer running an SDR, and you can forward with Netcat, SOCAT, or whatever you want, just routing UDP packets to another instance of SCAPI that will just process the sample. And that led us to our latest functionality that is not implemented yet. It could also ease us to build a cluster. Because sometimes with protocols, one SDR will not be sufficient. Sometimes you need multiple SDR to deal with high bandwidth and high frequencies. So maybe we thought UDP can be helpful to ease the way to bring all the packets to one instance of SCAPI and process that. Our custom header is pretty simple right now. The first byte, you have a total of 8 bytes. The first byte is the protocol ID, and 7 bytes are reserved for future use. We plan to put there the channel, for example, the signal quality, or anything that needs a per packet use. Why put the channel there is because sometimes on channel hopping or whitening, some protocols may use the channel number with algorithm to scramble the data. So it can be useful to be able to push the channel just as a metadata of your packet, so the SDR can know that it has to hop on another channel to send this particular packet. And we have defined several protocols right now. 0 is for invalid packets. Most of the time, invalid CRC. It's still useful when you develop things. To just grab those packets, you have Z-Wave, you have .15.4, which is the lower protocol for ZigBee and 6LoWPAN, etc. You have Bluetooth Low Energy, WMBus, and -7. And you still have a lot of room for other protocols. We are also providing you helpers, because each time your GNU Radio flow will receive a packet from the radio side, it will have to put that header in front of it. So we are providing basic helpers just a block to add a GR header and another block to strip it, respectively for the reception and the transmission of packets. You just have to put as a parameter the protocol ID, and that's all. And it will add the 8 bytes with 7 zeros. What we're releasing? We're releasing the modified version of SCAPI Radio, with all the protocols we have developed and tested under concrete equipment. And the corresponding new radio flow graphs for ETUS, for the ETUS board we have, for USRP2. Just be careful, well, if you want, for example, to modify the GNU Radio, the GRC files to work with, for example, the ACRF or the BladeRF, all you have to do is just run GNU Radio Companion, open them, and change the UHD sync and source block, which are dealing with the USRP, with GR Osmo SGR blocks, which can deal with a lot of other ones. So it's just simple as changing 2 blocks. And we're also releasing external tools around Z-Wave, passive Z-Wave discovering, so it will just sniff for packets and print out Z-Wave networks that it can sniff, and all the equipments involved in this home automation network. And an example of Z-Wave automaton that we will demonstrate later. There's still known limitations. For example, when you're dealing with dynamic channel hopping, for example, the USRP2 can deal with 56 megahertz bandwidth. BladeRF is limited to 38 megahertz. So if you think about Bluetooth low energy that uses 80 megahertz wide, you're just running a bit short of bandwidth. So that's one case where you need to have multiple SDR. And you cannot configure easily your local oscillator to just hop from a frequency to another. So the main idea is to listen wide. For example, the 56 megahertz bandwidth of the USRP. And you do multiple channel filtering and frequency translating to process all the channel together at once, instead of just hopping from one channel to another and have one just single flow line. Like I said, bandwidth limitation, both on radio side, like I talked, and also on computer side, because USDR is connected to the computer most of the time through USB port. So you also have sample limitation on that. One other limitation, it's pretty annoying, is GNU Radio does not tell you when the graph is running. You just launch GNU Radio, and it takes time to configure USDR, initialize all the blocks that are involved in the graph, and you don't have feedback. So right now, we are headed to have hard-coded sleep timers to wait for the graph to be set up. But there's no workaround for now. The overall setup cannot be fast. If you think of that, your packet will go from Python to C++ to Python to UDP to Python. Not very efficient in terms of timing dependencies. And it won't give you superpowers, but we may think of that later. We're working on that. As a disclaimer, if you want to transmit, don't forget to check your local regulation, because unless you're living on a Faraday cage, it might be illegal, or you need a ham radio license to be able to transmit. No, let's talk about a little bit about the devices we studied with our tool. So first, we started to assess Z-Wave home automation devices. So the devices we had a magnetic sensor, an alarm device, and a network controller. We used the open source software on a Raspberry Pi based on OpenZ-Wave. Unfortunately, OpenZ-Wave does not support the cryptography which Z-Wave supports. So everything was unclear. So the layer we provide you in SCAPI won't support cryptography because we did not have packet to test that. Side findings we had over the devices. Well, the first one is pretty annoying. If you transmit too fast, it crashes the software. It's not hardware related, it's just the OpenZ-Wave stack that is a bit crappy. So we have to hardcode timers again to just slow down the transmission. Even with going through Python, UDP, C++, etc., it's still too fast for OpenZ-Wave. And at some point, we wanted to reverse the firmware too about the ASIC. So the devices we're using relied on Zensys ASICs, the ZW301 ASIC, more specifically. Zensys seems to be the leader providing ASIC for Z-Wave, since it's the company that brought the Z-Wave protocol. And it uses a kind of crappy SPI protocol. So we added support in the GoodFET from Travis Goodspeed. So it's right now on the firmware. If you just download the firmware for your GoodFET, it will be on that. And if you want more detail about that, you can read our company blog that details everything we've done on the SPI protocol and implementing the protocol in the GoodFET. We also studied a Bluetooth low energy electronic cigarette. This one is from a French company, so as French people, we felt compelled to analyze it. It uses Texas Instruments system on chip. The firmware is really heavily based on TI examples. I think 80%, if not 90% of the code is taken from TI examples for sending the packets and over-the-air firmware upgrades. So it's pretty easy to understand that. Still, it was really difficult to audit that. Right now, the Bluetooth Low Energy only support the advertising, because once the device is connected, it hops really, really fast to 40 channels over 80 megahertz bandwidth. So with one SDR, we weren't able to sniff all the packets and follow the connection. And more, in addition to that, we had poor signal. Even with an Bluetooth and being at 2 centimeters away from the cigarette, we were losing packets. So that was the time when we thought about SDR clustering to get a wider spectrum to be able to analyze it. The potential threat we imagine on that, well, the first is privacy issues. Still not a good one, because sniffing consumption of your electronic cigarette might not reveal a lot of things on yourself. Maybe health issues, because this electronic cigarette can be configured from your iPhone to select between, I think it's 2 parameters of nicotine. So maybe if we can override this and send you a huge dose of nicotine, it will be a bit dizzy. You also have firmware corruption over the air. The protocol Texas Instruments provides in his examples allows the firmware to be ciphered, but they're not using it. It's just sent over the air in clear text. So you can easily think about writing a firmware based on the same TI examples the manufacturer has taken, and corrupt the firmware. And with that, maybe you can cascade the attack. Maybe you can hack the electronic cigarette to push a corrupted firmware and hack back the iPhone it is connected to automatically. We also studied XB UART bridges. Those are .15.4 protocols based. As the name stated, it's not ZigBee. So they're cheap and ready to use devices, just like your shield for an Arduino. You just plug it on your dev board and it's done. And therefore, they're very popular to electronic engineers, because they're ready to use. You have a bunch of software to deal with that. It's a custom protocol over .15.4, sorry. And we started the implementation of the layer, but we haven't gone through all the specificities of the protocol. So far, it's very rudimentary. And in fact, we discovered that .15.4 is used for 6LoWPAN, ZigBee, and XB protocol at least. And it's really annoying, because they thought about an underlayer, but they didn't give you a way to determine the upper layer. You don't have a field stating, well, above this, you will find ZigBee. So you have to rely on heuristic algorithms and it's pretty annoying. You cannot tell easily the upper-laying protocol. The roadmap of the development, well, the first line has been struck because it's already done. That's the XML RPC server. We also want to write a Wireshark plugin to be able to read back the PCAP that SCAPI is able to read and to read or write. Also leverage our header to put more metadata on it, and that function to handle a cluster of computer plus SDR. And of course, add more protocols. So how to add stuff? You choose a protocol ID. You build your graph in GNU Radio Companion to be able to read to receive your packets. Then you create a packet sync, which is basically a state automaton that will check for access code and remove invalid frames based most of the time on the CRC, and that prepends the GNU Radio header or use our helpers. Test it. Then you invert the graph for the transmission part, and you create a custom preamble block. It will prepend preamble bytes that are not part of the packet, and it will also add couples of null bytes at the end of the packet. You may wonder why this is necessary, and in our tests, we found that GNU Radio just shuts down the local oscillator of your SDR too early, so the last bytes are always corrupted. By adding extra null bytes at the end, we just leverage that to be able to get the last byte correct. You test it again and you're done. Then you move to SCAPI. SCAPI is pretty simple. You just write your required layers. Beware of predisect and post-build, because most of the time in computer-based environment, you have your header and then your payload. On radio, your payload is really often taken between the header and the CRC. So for SCAPI, you just have to predisect your packet to bring back the CRC to the header, so it can process packets smoothly. You test it and you're done. Then you have to tie together the GRC and SCAPI. You just put your GRC in your home directory .scapi/radio, and that's all. The tool will find it. But for that, do not change the top underscore block value of which is the default one for your graph name, because the tool will rely on that. You then edit scapi/layer/GNU-radio.py, and you bind the layers together. And optionally, you can just add your protocol in the list. It's just for auto-loading, but it's not necessary. You update the installer SCAPI, and of course, don't forget to send us a pull request for your contribution. And now it's time for Arnaud to show you the demonstration and talk about that. First, a disclaimer, we have to apologize. We really plan to do a live demonstration on that, but we discovered quite lately that the Z-Wave automation system we were using relies on European frequencies, which is 868 megahertz, and this band in the US is used for GSM. So if we were bringing the stuff and pouring it on stage, it will just infringe a federal law. So we moved back to video demonstration.
Okay, so in the left side. No? You heard me? Okay, perfect. So in the left side, we have our alarm system with the door sensor, the controller based on the Raspberry Pi and the OpenZ-Wave library, and the alarm itself. How does it work? When you open the door, it sends the frame to the controller, and the controller sends the frame to the alarm to turn on. And also, when you close the door, it sends frame to the controller, and the controller sends the frame to the alarm to turn it off. Of course, in a real alarm, you need to enter a password to shut down the alarm, but for demo purpose, that makes it easier. So a short video of the functionment, system working. Okay. Okay.
Even with video, you don't escape Murphy's law.
That's fine.
Okay, the virtual machine is frozen.
Okay, so we have to wait. So this is just a video of the system working, nothing as special. I will continue. In the attacker side, you can the PowerPoint also.
Sorry about that.
So let's take a short break.
Yeah. I'll have to restart the computer. VMware froze.
Yeah, so the system is working when you open it, start the alarm. So the attacks, we use the USRP and of course a Linux computer. And in the first time, we use the interactive shell. If you already use SCAPI, you have a shell like Python, and you can play, sniff packet, list, show, inject. So this is most for discovery. And also, you can script that shell. And we also introduce automaton. Automaton is a feature of SCAPI. It's well documented, and it's like a state machine. So you can do something like, I write a frame, when I have this frame, I launch another state, and in this state I send another frame. In this example, when we receive a frame to turn on the alarm, you send a frame to turn it off. But, okay. So I hope I can show that.
It's coming back.
Again, sorry about that. Pas les vidéos du coup. Non, black screen. Mais juste les slides. Okay, so no video because we have some trouble. So like I said, in the attacker side, we only need the USRP. This is all points of the tools and software-defined radio, just an SDR and a Linux laptop. Some details about automaton. Okay. Okay. The automaton, it's like a state machine. The first state is the initial state. We just, in fact, launch the SDR on Z-Wave. Like you can see the switch radio protocol command. It's a command we add to SCAPI. So you just have to change the parameter for ZigBee if you want ZigBee. After that, we jump to the waiting state. Like in name state, we just wait. We wait for the receive condition, and the receive condition is a switch on frame. This is a frame the controller sends to turn on the alarm. And when we receive that, we do the action, and the action is to turn off the alarm. Oh, so later. And like Jean-Michel said, we have to set a delay because we have some trouble with the Z-Wave controller if we inject frame too fast. Again, automaton are well documented in SCAPI documentation, and it's work the same way regular SCAPI and in SCAPI radio. Okay.
Okay, so where to get this tool? All you require is a GNU Radio 3.7. Be careful because the 3.7.5, which is the upcoming development version, just breaks the UHD blocks in a pretty nasty way. It's just the UHD sink, so the block that is responsible to transmit packets with an USRP. The first connection of this block used to be complex streams, so just the data that has to be sent. And they moved on the latest version to have 2 entries, but without letting the first entry being the samples. Now it's the second one. So the graph just doesn't work anymore. You just have to launch the graph and move the arrow to go to the second entry. GNU Radio 3.7 is already provided in Kali Linux or Samurai STFU, and you also need a compatible SDR, of course. Then you just grab the code from our Bitbucket repository. You go into the directory, launch install. You don't need to launch it as a root. It will automatically sudo when it needs to, and that's all. You have all you need to be able to deal with that. Thank you. If you have questions, you can go, and right after the question, I will try to just move the setup to show you the videos. Yeah. Yeah, sure. This one. Is there any question?
The tools will be online soon.
Yeah, the tool will be put online right after the talk, and the SCAPI modification. I've talked to Philippe Bionly, which is a coworker, and it will merge it into SCAPI mainstream. So hopefully all the SCAPI radio stuff will be available in the next Kali Linux or things like that. Thank you.
Thank you.